Okay, hello everyone, and welcome to this week's colloquium. Today we are pleased to have JC Viljoen. He did his master's at SAAO and Northwest University, and he's going to talk about determining the properties of galaxies in MeerKAT group. Thank you, JC, and the floor is yours.
Hi everyone. Yes, I'm JC, and that's my supervisor there, Dr. Magozzi, and my other supervisor, Prof. Loebscher, unfortunately could not join us today. And yes, I'll be talking about what I did for my master's, determining the properties of galaxies in MeerKAT groups. So,
You don't want to put people to sleep.
Firstly, what are we studying here? And we're trying to study galaxy evolution in groups, specifically through the H1 properties such as the distribution, the mass, and velocity. So, galaxy evolution. Here we ask the question of how do galaxies go from spirals, as we can see at the top there, to ellipticals, as we can see at the bottom. How do they go from blue and happy and star forming to red and dead and no longer star forming? How do they go from being dominated by rotational motions to being dominated by random motions? All of that. And the answers is firstly, in a big picture kind of way, hierarchical clustering, where we go from where small things form first and then combine to form bigger things. However, it's not just that simple, as many different processes can affect galaxies. You have internal processes such as feedback and strangulation, as well as external processes and environmental processes such as ram pressure stripping, mergers, and other interactions. So specifically, we're looking at galaxy groups here, and there's a reason for that. Groups form a very nice in-between environment. They're higher density than the field, where we just have one galaxy sitting on its own with not really much happening. And they're lower density than clusters, where we have galaxies in their hundreds, as well as hot intra-cluster medium, and there's a lot going on in those. So yes, groups host multiple galaxies, and they are dominated by tidal and galaxy-galaxy interactions, and other environmental effects such as ram pressure stripping is rare due to, in many groups, the lack of that hot medium that is present in clusters. As I said before, this study is done in H1, so neutral hydrogen. The reason for that is because galaxies have very large H1 disks. They're about 1.5 to 2 times the size of the stellar disks. And in optical, you might have galaxies just kind of sitting next to each other, and it doesn't really look like there's much going on there at first glance. However, when you look at the H1, it reveals that they're actually interacting, that these galaxies can actually be interacting. So yes, H1 can trace the history of interactions through things such as tidal tails, which we can see in images 6 and 7 and 8, and many of these actually. Through H1 bridges between galaxies, such as can be seen in image 2 between those two galaxies. Truncated H1 disks that can be seen in image 3, 5, 8, 7. Again, quite a few of these. And it's easy to see the kinematics using H1 images through things like moment 1 maps. We can see the rotation of galaxies. And the H1 cubes can be broken into multiple components, and thus revealing the disk gas and any anomalous gas in the system. So we're actually doing a follow-up on some previous studies of galaxies groups, specifically the QUIRES study done by Sarah Sweet in 2013 and 2016. This was an H-alpha study of 15 nearby groups from the SING survey. Yes, groups of SING galaxies, they sing together and form a choir. The original study used about a 15 arc-minute field of view due to, they used a 15 arc-minute field of view. They found that the groups in this system are late type dominated, they're gas rich, and they're in the early stages of assembly. Many of the groups in the study also feature multiple large interacting spirals, such as can be seen in this group. So this image that you see here is actually the group that I am studying. This is the composite image from the 2013 study here. Another follow-up on the QUIRES group was done by Zutar in 2019 and 2021, where they analyzed the H1 properties of these groups using ADCA and VLA data. They also conducted further analysis using WISE near-infrared data to determine the star formation rates of some of the galaxies in these groups and other properties. So the results from Zutar studies will actually be used for comparison throughout these studies. And again, this is the group in question in the image here. Specifically, this is the ATCA data on the contours here. So what are we doing with MeerChoirs specifically? We're doing an H1 follow-up study on the QUIRES groups using MeerKAT this time to give us a wider field of view, more detailed H1 observations. This then reveals fainter gas and possible additional group members. I actually did the imaging for this group myself, and I won't get too much into that. It was done using the hierarchical pipeline on Ilifu. There wasn't too much noise to flag in this data, luckily. Only one antenna gave some problems, and I ended up choosing a 0.7 Briggs robustness weighting for a nice balance between detail in the observations and fainter gas, as we do need both. This is the main result of this work is the H1 image, and there it is. The H1 image itself is in the contours there. And the background image is the G-band image from decals. So looking at the central region of this group, we can see a strongly interacting pair of spirals termed S1 and S3. And these are connected via a tidal tail visible in multi-wavelength observations. We can also see two irregular galaxies, S2 and S6, and S2 here forms part of the central interaction. We see a potential tidal dwarf galaxy, S7, which is also involved in the central interaction. We see an SB0 type starburst galaxy, S4, and that one is showing signs of H1 deficiency. We also see a regular normal everyday spiral, S5, and a spiral dwarf, S10. So in the original H-alpha study, S10 showed signs of interaction with another galaxy, S8. However, we failed to detect that galaxy in this study. Another galaxy that we failed to detect, but I labeled on here anyway, is S9, which is an irregular dwarf. Comparing these...
I don't want to interrupt, but so I saw you're about 3 hours on source or something with your observation. I mean, like the RMS millisecond per beam there, 0.35. I mean,
yes.
Like roughly what column density can you get down to at like a few sigma with that kind of observation time, just so you get some idea of like how low surface density things you can see?
So my lowest column density, I did actually calculate that, but I did forget to put it in this talk. I'm so sorry. I will check for you after, if that's okay, because I can't remember the number off the top of my head. Sorry. But yeah, it's about 3 hours of total integration time in this image. Where were we here? Observations, comparing my observations to Zuzar's observations here. And we can see that the MeerKAT image definitely does improve upon improve on the previously done imaging. We can see the bridge connecting S2 to S1 there much better. And we can also see some tidal tails below S3. Comparing some parameters, we did end up achieving a smaller beam size of about 20 by 15 arc seconds versus about 45 by 25 arc seconds. And we also, this gives us some better resolution in our images. We also achieved a lower.
Just quickly, is that an ATCA image?
So this one is ATCA.
Right.
And this one is MeerKAT.
Sure. But I mean, the VLA would have done better than ATCA.
VLA would have done better than ATCA, but not all of the groups that Zuzar studied were studied through VLA. Some were done through VLA and some were done through ATCA. So yeah, I unfortunately don't know what determined choosing which group gets which data from which telescope.
We'll confirm on the calculation. Yeah.
Is it okay?
Yeah. And yes, we achieved a lower RMS of about 0.35 millijansky per beam versus 1.6 millijansky per beam. So with our lower RMS, we get better sensitivity, which allows for the detection of all of that faint gas in the first place. In addition to all the faint gas, of course, it's being buggy now. There we go. Sorry, everyone. That was just my computer deciding that the internet doesn't work anymore. But we're back and resuming where we left off, which was the detections for S7 and S10. Moving on, we detected several potential new members in this group using, and we used the label of MeerKAT for the new MeerKAT galaxies. We detected 9 of them, all listed in the table here. And some notable new members in this galaxy are MeerKAT 11 at the top left there. Top right from everybody else's perspective there, which is a Safer 2 galaxy, and MeerKAT 12 at the bottom there, which is a low surface brightness galaxy. Now, it does look like there's another galaxy in the tidal tail of MeerKAT 12 there, but upon further inspection, that galaxy is actually in the background and not part of the group. So we determined H1 masses for all group members as well as the original 15 arc-minute field of view, and we found higher H1 masses for several of the members and that field of view. So this these higher masses, in this case, the higher masses are due to the increased sensitivity of MeerKAT when compared to other telescopes. However, we also detected a higher mass for S1, but a lower mass for S3. And this is mostly due to gas reassignment, as you could see in the previous images. When looking at that central region, the H1 between those galaxies is quite intermixed, and separating them is a bit hard and will not necessarily give consistent results between studies done by different people. Comparing the H1 masses to the stellar masses, we find that galaxies with higher H1 masses tend to also have higher stellar masses, except for the case of S1, S4, and S10. S10 has a really high stellar mass there. I don't really know why. S4 is known to be H1 deficient, and this mostly explains the mismatch between the H1 mass and the stellar mass. S1, however, has the highest stellar mass and highest star formation rate in the group. And this high star formation rate is due to its merger with S3, triggering star formation in the tidal tail between them. So finally, the central interaction, the big part of this group, where a lot is going on, is what we can see here. As you can see, it is connected by a tidal, S1 and S3 are connected by a tidal tail visible in the optical there. And yeah, S2 is connected by that gas bridge. And as can be seen in the moment one image on this side, the gas disks of these galaxies overlap greatly. We did try to separate them because of the great overlap of gas disks in this galaxy in this system. Software kind of failed for trying to do this, so it's done mostly visually, taking the optical sources into account. To effectively cut out the gas belonging to S1, we selected gas with a velocity between 7,800 and 7,950 kilometers per second on the red fast-moving side of this galaxy, and between 7,650 and 7,800 kilometers per second on the slow-moving side. Similarly, for S3, we used velocities higher than 8,000 kilometers per second on the fast-moving side, and higher than 7,925 on the slow-moving side. Yes, that means that there is a bit of an overlap between the images, between these cut-out images in the galaxies. And to cut out S7 from S1, we simply selected velocities. We simply selected pixels with a velocity of lower than 7,800 kilometers per second. Okay. So what we're trying to do next is to model these individual galaxies and try to see what's going on there. First thing we have to do is assume that the gas in these galaxies does in fact form a disk. However, we do know that they're not purely disks. They are made up of multiple components, and that requires additional modeling. The disk modeling in this case is only done after the visual separation, as otherwise the entire S1, S3, S7 system is interpreted as being only one H1 disk, making everything else much more complicated. The first technique that we use for modeling is 3D tilted ring modeling, and this basically takes the galaxy's gas disk and try to model it as a set of rings with distinct geometric and kinematic parameters. So for each ring, we'll have an inclination, a position, angle, things like that. And then we compared these modeled systems to the real H1 data. This gives things like rotation curves, and it also gives us maps and diagrams comparing the detected sensitivity, velocities, velocity dispersions, those type of things. And yeah, the 3D tilted ring modeling in this case is done using 3D Barolo. Yeah. Here we have some results of that, looking at S1 specifically. And we can see that looking at the velocity column there on the residual side, it has high residual velocities near the center of this galaxy, which is quite interesting. It's about 100 kilometers per second in the appropriate direction on each side. We also see high residual velocity dispersions in this galaxy of about minus 20 kilometers per second near the center and positive 20 near its near the area where it's merging with S3. So that dispersion near S3 is almost definitely due to the merger there. However, the central dispersions is still to be determined. Looking at S3, we can again see that there are high residual velocities and velocity dispersions near S1, and this is again due to the merger. Other than that, there's not much weird going on here. And finally, looking at S2, we can see that there are high residuals around the edges. Now, remember that S2 is connected to S1 by that H1 bridge, so it may be accreting gas from S1 in this case. And we did model several other members, but unfortunately not all of them. And from this, we found that the central galaxies have mostly kind of similar systemic velocities, indicating a proximity to the same plane that they're actually touching. The systemic velocities for all group members were determined to be lower than what was previously reported, what was reported in previous studies. Most galaxies are found to be intermediately inclined, and you'll see the star there in the table. That is because MKT12 have different inclinations between different rings, showing signs of warps. The next technique that we use to try and analyze this group is Gaussian decomposition. And this models the spectra. This takes a spectrum and it tries to model it through fitting Gaussians to that spectrum. And this allows for the identification of different gas components, each of which can be defined by its amplitude, mean velocity, and dispersion. Having these different components allows us to separate this gas from anomalous gas in the system. The Gaussian decomposition is done using Gauss pi plus. However, Gaussian decomposition on its own does not tell us what is this gas and what is anomalous gas. We need to combine techniques to do that. Specifically, we combine the 3D tilted ring modeling with the Gaussian decomposition, as the 3D tilted ring modeling gives us an idea of what is this gas. That is used to identify this gas, and then from that we identify other components. We determine what the other components are. So there are three main identified components here. First, the disk. Second, the leading gas, which if you take a look at the top plots in this slide, the leading gas has a slightly higher rotational velocity than the disk gas. And the third component is lagging gas, which has a slightly lower rotational velocity. However, it is sometimes a bit difficult to determine whether a component is leading or lagging gas from only looking at the Gaussian plots here, as the velocities on the Gaussian plots are line of sight, meaning that the leading or lagging components could be on either side of the disk. And
question, your continuum there is so way below zero. Should your fix sit at zero for its continuum? Understand what I'm saying?
So that just kind of happened with a lot of the spectra in this system. I'm not quite sure why. I did try to make, yeah.
I was wondering, are you sure? So when we do this, at least in the data direction, we're cleaning, and then you want to make sure that sort of you don't over clean, you don't kind of remove signals. So are you sure that you didn't over clean too?
Yeah, I mean, however the data were reduced, I'm not talking about just the fit, obviously not fitting outside of the lines. But anyway, that's like not to worry about now until the next thing right here.
Okay. There's also a lot of gas in this group for which we don't detect any Gaussian components. And that gas is termed non-disk anomalous gas, or NDAG. So anywhere where I just say anomalous gas, or where the term NDAG happens, that's gas with no identifiable Gaussian components. And this kinematic separation, as well as the Gaussian decomposition, is done for each individual pixel in the central interaction. So we can then create a model image for each component. An example, not quite there yet. Through this Gaussian decomposition, there are four interesting points. First, the area between S1 and S3, where the optical tidal tail sits. Point B would be the area between S1 and S3 away from the optical tidal tail. Point C would be the area between S1 and S7, and point D would be where S1 connects to the gas bridge. Now, taking a look at the spectra here, we can see that at point A, we have three identified components: a disk component belonging to S1 and S3 respectively, and a shared component between the two. Looking at point B, and at this point, S1 and S3 have very similar velocities, and the disk component here could be belonging to either S1 or S3. Looking at point C, the point between S1 and S7, we see something that might be a component for S1's disk and something that might be a component for S7. However, we have a very low signal-to-noise ratio in this entire area. And finally, looking at point D, we see a component for S1's disk and a leading component. Now, those model images I mentioned before, here is an example of one for the anomalous gas in this system. So this is gas for which we did not detect any Gaussian components. This makes up about 20% of the system mass, and this this high amount of anomalous gas is due to the high levels of interaction in the system. Because we have that merger between S1 and S3, we have S7 being a potential tidal dwarf interacting there, and we have that interaction through the bridge between S1 and S2. S7, the dwarf in this case, is mainly being tagged as anomalous. Looking at the different components for S1, we can see that the peak emission for this galaxy resides roughly where the optical tidal tail is. However, we do see high amounts of leading and lagging gas on both sides of the galaxy. The peak leading emission in this galaxy is also near that tidal tail, and it may be contributing to the star formation. And the peak lagging emission in this galaxy is, interestingly enough, near its center. Looking at S3, it is significantly influenced by S1. However, the peak emission is still mostly optically matches S3 in this case. We identify both a leading and a lagging component in this galaxy, with the leading component being mostly on the receding side of the galaxy and the lagging component mostly on the approaching side. And for this galaxy, we modeled almost all of its gas through this technique, so 98.8%. Finally, for S2, there are quite high amounts of non-disk anomalous gas for this galaxy, making up about 18% of its total mass. Again, this may be due to gas accretion from that bridge. We see a very small amount of leading gas near the center of this galaxy and almost no lagging gas in this galaxy, less than 1%. And we modeled about 78.8% of the total mass of this galaxy. And that is it. So in conclusion, we improved the imaging for this group, detecting faint gas, making detections for S7 and S10, and as well as 9 potential new group members. We detect higher H1 masses for many of the galaxies, as well as the original field of view, and this is most likely due to the increased sensitivity. Only MKT12 shows signs of warps when looking at the 3D tilted ring models. We identify S2 as part of the central interaction because it's connected to S1 through that gas bridge. And we deconstructed the H1 of the galaxies involved in a central interaction, finding high amounts of non-disk anomalous gas throughout the entire interaction and high amounts of leading and lagging gas in S1 and S3 due to the merger. Even though I am done with my master's, we are not done with this group or with MeerChoirs yet. So what's next would be a multi-wavelength analysis using WISE data to determine star formation rates for all galaxies in this group, and using salt spectroscopic data, specifically long slit to determine metallicities, IFU data to get an idea of some optical and IFU data to get an idea for some optical kinematics. The SALT data for this has already been partially taken. We plan to do a simulation of the central interaction in this group to try and get an idea of what this interaction looks like over time. And finally, if there's time, we will compare this group to a second group, one that is post-interaction, so we can study the different stages of galaxy evolution in groups. Thank you. Question time.
Thank you, JC. Great talk. And congratulations on doing this job for your master's. Okay, any questions? Both online and in the room.
Yes.
Congratulations, it really lovely work.
Thank you.
Just to follow up on the SALT data, have you already tried taking the IFU data with the SMI?
We've not taken the IFU data yet, so it's long slit data for some of the central galaxies that has already been taken. Yes.
You mentioned that the DUSA people had already looked at the WISE data for the kinematics. So you mentioned doing that again. Is that, can you explain why?
Yes. So we're looking at the WISE data again because DUTAR only determined star formation rates for some of the central galaxies and none of the additional galaxies. So we are going to be trying to fill in that gap a bit. Yes.
I think if I remember right, you maybe had one of your MeerKAT detected galaxies that didn't have an optical counterpart. Is there a dark galaxy that's detected in H1?
That would be S9, the galaxy that's below our detection limit there. And yeah, finding an optical counterpart for that has not been successful so far.
You show us where it is. Yeah.
I came prepared.
Not lying anyone.
So it should be like right there. For people online, it should be like right there. In this region. But as you can see, nothing.
So I think we're also talking about in the opposite of that, right?
Oh, possibly, yeah. So that one is not seen in the. There's some that are seen in the optical, but not in H1, and others that are seen in H1 and not optical.
Yes. So.
Is this optical?
So in this image, the blue is H1 and the yellow is optical. And this was just a quick overlay of the moment zero that I did in Photoshop. So, yeah. Yes.
So your second most massive H1 galaxy wasn't detected in the original work. I'm just wondering how could that be? It was like more than 10 to the 10 solar masses, and why wasn't it? Given they were detecting much lower H1 mass galaxies than that, was it outside their field of view, or is that
yes, yes. So in the DUTAR work, only these are in the field of view, and in the studies by Sweet, only these are in the field of view. None of the rest that we've got going on here. So yeah, outside of field of view. Yes.
So for a galaxy slave person, you're going to do you're going to compare kinematics from optical and radio data in your future work. Well, why could they be different?
So the reason for that is details.
So
the reason for that is details.
Out in the radio, right?
Yes, we detect further out in the radio, but a radio, yes, we get better angular resolution in optical. Yeah.
And they're different phases.
Different phases of gas as well, yeah.
Yeah, but they'll be moving the same, right?
They should be moving about the same, but that is to be determined.
There's weird stuff going on in the bottom galaxy there with the sort of the leading and the lag. Do you have a sense of leading you to the contentious relationships? Is there any other effects besides star formation happening in these?
In this one with the leading and the lagging gas near the center. So I actually took the slide on that out. But this galaxy is also an emission line galaxy with previously studied AGN. However, I didn't quite get enough time to explore that aspect of it in my master's. So this lagging gas near the center of it, as well as the central dispersions in this galaxy in the freely tilted ring modeling shown earlier. I'll go back to that slide as well real quick. As well as the central velocity and velocity dispersion residuals. May very well be due to that. but I don't quite know. I didn't look into it very much. Yes.
I was just wondering also why the intensity is so much higher, and that, I mean, that's presumably because of the interaction, but you already see the disturbance in the velocity there.
Yeah, no, that is quite interesting. That we do have a lot of high intensity near the bottom of this galaxy, but the velocity is not as disturbed. Yeah, I think we just have a lot of gas sitting at the bottom, but it's still moving mostly with the galaxy. So, yeah.
Was it possible to a lot more gas, but it's ionized in some other states?
I mean, if it was ionized, if the extra gas was ionized, we wouldn't see it in H1. I'm so sorry. Can you repeat?
It could be, or it's molecular. It's the only other way to molecular gas. You'd think that the peak would be in the middle.
Yeah, one would think that the peak would be in the middle, and this is also part of why looking at optical kinematics would be useful, as we'll get a more complete picture in terms of this.
Was there any ALMA observation you can look at things?
I don't know.
You know, the star formation correlates with the peak in H1.
Not in that much detail. I know that in terms of star formation, that galaxy S1 does have the highest star formation in the group, as we can see, about twice as much as the galaxy with the second highest. And most of that star formation is probably happening in the tail there, in that tail between them there. So, yeah.
Right. If there's no question, let's thank JC again. Thank you, everyone. See you in the next colloquium.
Thank you.
Yeah.